This is, of all the things I teach, this is the thing that's probably going to make the biggest difference to your A-level score. Exam techniques then. Um, Exam techniques are anything that's really not physics that will help you to improve your A-level score. And there are some exam techniques that you absolutely have to get right in order to do well in A-level physics. So obviously you've got to have a certain amount of maths. That's not really exam techniques, that's almost physics. I mean, physics is applied maths, so we're not going to deal with maths stuff. I'm not going to deal with graphs and interpreting graphs. What I'm going to deal with is the words in the questions that tell you what to do. So we are going to talk about command words. So explain, discuss, calculate, deduce, justify, compare, all of those command words. We're going to talk about some of those and the ones that come up most frequently, and how to structure your answers for those. I'm also going to talk to you about exam techniques in general. So let's start with this, okay? Most papers, not all, but most papers are split into two. So quite often there's a multiple choice section and a structured questions section, or short answer questions section. Sometimes the AQA paper 3 is a practical paper and then the option topic, different papers, but there, I mean, you can swap over from one to the other whenever you like. And so within an exam, there are different sections. And one of the things that you've got to get your head around is that you've got to decide when you're going to swap from one section of the exam to the other one. And you need to know this in advance so that you know if you're running slow and that you should move on now. It also means that if you have in your armoury knowledge of your own scoring rate, either marks per minute or how many, I suppose you could do minutes per mark. It's up to you which way round you want to do it. It could be marks per minute attempted, or it could be marks per minute achieved. Now, those two are different. You need to be aware that if you attempt lots and lots of marks, but you only get a few, then maybe it's sensible to slow down a bit so that maybe you score a few more and you don't kind of burn through all the available marks and not score the marks for it. So you need to have how many marks per minute you can score on each of the sections of each of the 3 papers in your exam. Now, you need to then figure out when is your optimum swapping point. Now, obviously, there's going to be a certain amount of probability here. So you might normally score at, I don't know, 50% of the marks or something. And do it in, you know, 1 minute 17 seconds per mark. You might, or you might on this occasion not do anything like so well, and consequent, right? But what you've got to do is you've got to know what's your normal scoring rate. What is your normal marks per minute for structured questions on paper 2, okay, and what's your normal marks per minute for multiple choice questions on paper 2, okay? And can you see you can then, if you know those numbers, you can kind of work it out. I mean, you don't have to do fancy equations, you can just kind of plug some numbers in. Right, if I score 50% on these ones and I score I don't know, 45% on these ones, what point do I swap over in order to get the maximum mark? right? And you can just plug the numbers in and see where you would, if I did it for this long, this would give me this many marks on this section, and I'd get this long on this section, and this would give me this many marks. That would give me a total of this. Whereas if I shortened it by, I don't know, 10 minutes, what would that? You can find the optimum, the maximum mark score, and you can then decide that you're going to swap over at that point. Now, obviously, in the real exam, there might be extenuating circumstances that means that maybe it's a bit better to adjust it. But you need to know what your best option is before you go in. You need to have a game plan before you go in so that you can optimize when you swap from one section to another section. Okay, right, now the next thing to say then is, if there is a section where you score particularly poorly, then you need to put that right. And when I say section, I mean it might be practical questions, or it might be particle questions, or it might be multiple choice questions, or it might be wordy questions, with explain, describe, compare, or it might be difficult calculation questions that cause you the problems. In which case, then you've got to figure out how to put that right. Maybe your score in multiple choice questions is actually really good, but you spend about 3 times as long on them as you should. And if that's the case, then what you need to do is to improve your odds in multiple choice so that you can operate more quickly. You might not score more for the multiple choice section, but if you can do it quicker, that gives you more options of scoring marks on the structured questions, which you can't guess, right? Multiple choice questions, if you run out of time, at least you can just put dots somewhere randomly, okay? But you can't guess the structured questions, so if you don't get to them, can you see? I would always recommend that you do your structured questions first and then your multiple choice questions second, whatever order they appear in the paper, okay? Right, now, all of this is, they're all of them exam techniques. They're all of them going to require that you study what you need to do in order to maximize your score. Okay, that's the game you're playing, and I hope you realize that what you're doing is your currency, if you like. It's not pounds and pence, it's minutes. You're handing over minutes, and in return you want as many marks as you can get, please, so that at the end of your fixed time, because you can't extra time, right, at the end of your fixed time you scored as many marks as you possibly can. Now, if you start running out of time, then you need to work on improving how quickly you work. If you get to the end of your time and before the end of your time, and you've finished answering all the questions you can, then at that point you need to work on how to score more on the questions that you're attempting. Right, now, of all the different things that you could do that would improve your score, there are 2 things that absolutely refer to pretty much everybody. If you were to improve these things, you would score better. The first is you have to read the questions properly. And it's very easy for a teacher to go, right, read the questions carefully. And everybody goes, yes, I'm going to read the questions carefully. And the teacher says afterwards, you didn't read it carefully, did you? Because you missed that it was each second, or you missed that the nucleus recoiled, or you missed that you could ignore air resistance, or you missed whatever. And you'll go, but I did read it carefully. And you didn't read it carefully. Right, now, when you are reading an A-level physics question, you have to think that this is not really like reading anything else. It's not a novel. It's not a newspaper. It's not even TikTok captions. What it is dense data that you can then use to solve a problem. Now, the dense data you need to treat like a table, maybe with names and addresses in it, and you've got to find your friend Freddie, right? You've got to look and you've got to find the right information that will tell you your friend Freddie's telephone number, okay? Or you've got to find the potential difference across the plates, Or you've got to find how to go from capacitance to not charge but current. How am I going to do that? What route am I going to take? Right now, this is problem solving, and the information is there in the question. What you've got to learn to do is to, well, first of all, not miss anything. Second of all, be able to interpret the data that's there. And third of all, when you've got data that's in the form of instructions, that you can follow the instructions properly, every instruction, so it tells you what to put. You should get to the point where you understand the questions so thoroughly that they become instructions on what you should write. And you can predict what's on the mark scheme because you're going to write it. Whether it's a calculation or whether it's an explain or whether it's a deduce or whether it's a determine or plot or draw or compare or whatever it is, it's a set of instructions on what you should do. That's what you've got to get to that point. Right now, all of you, you're all really good at pattern recognition. Almost everybody is doing maths as well as physics. Most of you are doing a mathsy third subject. Things like economics, computer science, chemistry, even geography is a science, right? Honestly, most of you are doing maths, further maths, physics, or maths, physics, computer science, economics maybe. Most of you are doing nothing but numerical subjects. And what that means is that you're really good at spotting patterns in numbers, but you don't look at the words carefully. You don't do what it says to do. Right now, in order to do what it says to do, you have to understand what is meant by each of the command words. Right now, there is, for all of you, I think, the Essential Exam Techniques course is available to you on your in your work area, your membership area. Right now, I'm just going to oh no, I need to share it, don't I? I'm going to share my screen. Okay, and I'm going to log in as myself. Obviously, not all of you are going to have all these courses, but I've got more because I made them. So the one that I want you to look at is the Essential Exam Techniques course. You can either look at that one or you can look at the Easter one if you've got it. Right, so Essential Exam Techniques course. Right now, this course has got, it was 8 weeks, some of you were here, and it's 8 lessons on the really essential bits of exam technique. So the first one is how to read the questions. Okay, so this is how to avoid missing things. I'm not going to do that exactly today. I am going to kind of use it. Lots of you have been through this already. If you haven't been through it, please, please, please do. The Ninja Question Analysis is also available. If I go back to my website, I go through the Ninja Question Analysis in quite some detail, with lots and lots and lots of examples in this Fields and Forces Masterclass, which is totally free, and it's in the free stuff bit of my website. So go and look at the Fields and Forces Masterclass, and I will go through all of the Ninja Question Analysis, and then I demonstrate using it over and over and over and over. And some of them are year 12 questions, and some of them are year 13 questions, but you ought to be able to cope with most of them. I chose the year 13 questions so that you could go through them with just a little bit of extra knowledge from year 12. So you should be able to do the questions in this masterclass. Stop when you get bored, because that means that you're not learning anything anymore. So I'm not going to do the Ninja Question Analysis today, but I am thinking that I will go through the command word scaffolds. This enables you to look at a command word and figure out what you've got to write. Okay, so I'm going to click on there, and the command word scaffolds then, can you see if I click on that lesson, there's a video, but we're not going to watch the video, obviously. You can watch that whenever you want, but there are some resources here that you can use. Okay, so so different command words, right? So the first thing I'm going to show you is the command word frequency. Some of you have seen this already. This is just anecdotal evidence of which command words are most frequently used. So explain is up there. In fact, calculate, if you include all of the calculate derivative words, calculate, determine, show that, deduce, those ones together are the biggest category. So calculate, unsurprisingly, is the thing that you have to do most often in A-level physics. Then after that, the next most common command word is explain. State is up there, especially for AQA, but state is only ever one word, one mark rather, which means that the state, if you were to weight these frequencies by how many marks it's worth, state would come much further down. So calculate, determine is up there, show that is up there. Can you see the next one, the wordy ones? So the wordy ones are the ones that people struggle with. So explain, then describe, then derive, draw, suggest. Can you see all of these? They're all really quite unusual. Okay, now Edexcel questions on the whole are relatively straightforward, but they use more different command words than the other exam boards. So if you do calculate and all the derivatives, explain and describe for OCR and AQA, the chances are you'd be able to do at least 80% of all the questions on the paper. If you're Edexcel, you also need to be able to do justify and assess and criticize and compare, because they come up more often on Edexcel than they do on the other two. Okay. Having said that, like I said, Edexcel questions, they're more straightforward. Certainly they're more consistent. They have fewer twists in them that try to catch you out. So yeah, if you're doing Edexcel, you're great, you're in good shape, because they haven't made any mistakes in the last 3 years, whereas the other exam boards have, and they've been told off for it by the Institute of Physics. Right, so frequency wise, explain and describe are the two most important command words, apart from the calculate, show that, determine ones. Okay, so right, I'm going to close that. Right, now the next thing that I want to talk to you about then is, what's this one? This is a spreadsheet that has got examples of different command words. So if I make the command word box a bit bigger, can you see there's links to papers, AQA, and then Edexcel, and then OCRA. Okay, and you can see that they're for 3 different years. And the first one is paper 1s, the second one is paper 2s, and the third one is paper 3s. Now, you've got all of these already, but what's different here is that you can have a little look at this and you can see that there's an example of a calculate and an estimate and a describe and an explain, okay? And in here, ooh, let's make that a bit bigger. You've got identify and show that and determine and describe, right? So you've got, all I've done is just pull out some papers which have got different examples of different command words, and I've made it clear which ones come up in that paper, which questions they are, so you can have a little bit of a practice. Right, now, the next thing I'm going to do is I am going to choose, shall we do an explain? Can we go to an explain? Right, so we've got, I'm going to choose Edexcel 11A explain. So I'm going to pick that question paper. So I'm going to do control and click, and it's 11A that I want. So that's a bit small, so we'll make it a bit bigger. So this is explain. This is a classic explain question, and it is worth, can you see, 3 marks. Now, can anybody tell me the structure for an explain answer? Pop it in the chat.
Key fact, consequence.
Brilliant. Key fact, consequence. Oh, I just realised I've had a question about criticise. Okay, so usually criticise is associated with practical questions. You might be given a table of data and they want you to criticise the data. And you'd have to say, well, there's only 5 points and you really need 10. You'd have to say the number of significant figures or decimal places isn't consistent. There's no units in the column headings. I don't know, maybe it's not a big enough range of temperature. You need to criticise it. Okay, it does come up in other papers, but not that often. Okay, Viva? Right, so explain then is key fact, consequence. Now this is 3 marks. So we either need 2 key facts or we need 2 consequences. But that's the structure of an explain, and you need to know the structure of every command word. Right, now we have to explain the shape of the graph. Okay, so we've got a cyclist on a horizontal lawn. The cyclist starts from rest, there. They produce a sketch graph of the velocity v of the cyclist against time. So what is happening with time to the velocity?
Well, the velocity is increasing.
Right, so the velocity is increasing to begin with. Then what happens?
Well, then it plateaus and it gets to a constant velocity.
Okay, so the velocity increases, and then the rate of increase slows down, doesn't it? It's yeah, and the rate of increase gets less until it reaches a constant velocity, yeah? Right, now if I wrote that for this question, I wouldn't score anything. Why not? Have I explained anything?
No, you described the graph.
I have described. Perfect. Can you see that the mistake is to describe, not explain? Okay, right now, Ian has said the rate of acceleration decreases. I'm going to be really mean, Ian. Acceleration is already a rate. It's the rate of change of velocity. The rate of acceleration is actually called the jerk. So you need to be careful with your language. The rate of change of velocity is decreasing. In other words, the acceleration is decreasing. Okay, so be careful. Is that okay? Good. Right, now, what we've got to do is we've got to explain the shape of the graph. Right, now, when the velocity is increasing, we've just been discussing with Ian that the acceleration is the rate of change of velocity, isn't it? What is the acceleration on this graph? What gives us the acceleration? Because it's not an acceleration time graph, it's a velocity time graph. Thank you, Ian. It's the gradient of the line. Right, now, what causes acceleration? Yes, 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 cooking with gas. A resultant force is required. Yeah, so well done. A resultant force is required to cause acceleration. Right, now, can you see what the instructions in this question say? They say to explain, that's key fact consequence, the shape of the graph. So we have to explain how the velocity is changing. But we also have to explain why the velocity is changing. And it says include force in your answer. It says to include it. If you do not refer to force in your answer, you cannot expect to get 3 marks. Can you see? You must follow the instructions. So, in order for the acceleration to be big at the beginning, what must be true about the force?
Like the greatest magnitude.
Yeah, so there must be an unbalanced force, a big one, at the beginning. Okay, so can you see what the key factor's got to be? What's our key fact here?
Resultant force acts on the
Right, so at
cycle.
t equals 0, there is a large resultant force. Yeah, which causes an acceleration. And the rate of change of velocity, which is the acceleration, is large. Right, you could say acceleration if you want in there. It's large. Right, now, can you see what I've just done? I have written that bit in green is a key fact. And the rest of the pink is a consequence, isn't it? I'm going to put it in an orange box. That's a consequence of the first key fact. Can you see that? So if you've got a large resultant force, you're going to get a large acceleration. And really what we ought to do is say F is equal to ma. Does that please you, Ian? Yay, good. Right, now, can you see then, we've now got to not just explain the beginning bit of the graph, we've got to explain the fact that the acceleration gets less. Not the velocity gets less, the acceleration gets less. Why would the resultant force decrease?
Drag or friction.
There we go. So now can you see that we're talking about drag increasing with increasing speed? Now it might be drag with the air or friction with the air, whatever you choose to call it. Can you see we are referring to another force? Oh, that's good. Can you see my next key fact is as the speed increases, the drag or the friction increases. I've run out of room, so I'm going to go up here. So as V increases, okay, the drag or friction increases. Right, so there is my next key fact. Woohoo! Right, so what's the consequence of the friction increasing? What happens to our resultant force? Well, eventually it becomes equal, yeah. So the resultant force gets smaller and smaller until, can you see, resultant force gets smaller and smaller until, yeah, the driving force and the drag equal each other, yeah, until the driving force equals the drag. Right, now, can you see that this is a consequence of this one, but it's also a key fact for the next bit. What is the consequence of the driving force equaling the drag?
Zero resultant force.
Yeah, in terms of the thing that we're trying to explain the shape of?
Oh, constant velocity.
Yay! Cooking with gas. Cooking with gas. Okay, so yeah, so then can you see my final consequence is that the velocity becomes constant. Right, now, how exactly the 3 marks are split up, but can you see the structure here? We have to explain the shape and we must use force to do it. So we have to have a key fact that includes force. And our key fact, F equals ma, we've got a large resultant force, we get an acceleration. When V increases, the drag or friction increases, the resultant force gets smaller until, yeah, can you see? Key fact, consequence, key fact, consequence, all the way through until we've answered the, we've described the entire shape. Okay, Newton's first law of vibes for the very last bit, yeah, the terminal velocity, or really in this case, top speed. Okay. Right, now, let's just go and have a quick look at the mark scheme for this. So I need to go back to mid. Right, so it's just this bit. Right, now it's 3 marks. So you have to say that there's an initial acceleration due to a resultant force, that's worth 1. Decreasing acceleration as a result of resistive forces increasing, or decreasing acceleration as resultant force decreases, that's worth a 2nd mark. And then the 3rd one is no acceleration as the resultant force is 0, or constant velocity as the resultant force is 0 in the third, for the 3rd mark. Can you see you had to describe those, explain those 3 different sections of the graph? And the marks are really clearly explained. Can you see? Okay, we did it to death. We did quite a substantial thing. Right, now, I hope that has helped you a little bit with explain. Right, so the next one that I wanted to do is not explain, but describe. Let me go back to this one. I want to describe. Right, so I'm going to use this AQA. Question 3.3 is describe. Ooh, bit big. So 3.3. Okay, so first of all, we've got to read the other bits of the question so you can understand what it's talking about. Okay, so figure 2 shows a ray of monochromatic, that means single colour, single wavelength, green light, incident normally on the curved surface of a semicircular glass block, and it's at the critical angle because we've got an angle of refraction of 90 degrees. Okay, and it says calculate the angle of the ray on the flat surface of the block. So you've got to figure out that's your critical angle, but they want that angle, theta. Okay, so you've got to get theta and then subtract it from 90. Okay, so you've got to get critical angle and subtract it from 90 to get theta. Right, now, that is the first bit. Okay, so you're going to do that. Then there's another calculate. Now we've got a thin film of liquid. So instead of using the sine critical angle is 1 over the refractive index of glass, now we have to do sine critical angle is 1 over. Now this is the liquid and this is the glass. Okay, so we've got the angle of incidence is changed so that the angle of refraction of the green light is again 90. So we've now got a new critical angle, and we've got to calculate the refractive index of the liquid there. Okay, so we do that, doobie-doo, doobie-doo, doobie-doo. And then we've got 3.3, which is, it's describe and explain. It's not just describe. Can you see the command word? Right, now we know how to explain. So we've got to describe and explain now. So we're going to do the key fact consequence for our explain. What can we do for our describe? What is the structure of a describe answer? Can anybody help me out here? It's an English word, guys. What does describe mean? If I said describe, I don't know, my mouse. Yeah, it's what you observe. It's what you see, right? So I'm going to stop showing a minute so that you can see my mouse, right? Describe my mouse. Say about it. It's red. It's not just red though, is it? And black. Good. Red and black. It looks pretty partial to cheese. You're not taking this seriously. It hasn't got a tail either. It's got chopped off like 3 blind mice. But anyway, yeah. So, yeah. So right now, your when you write an answer, it's a weird semicircle shape. Yeah. It's meant to be ergonomic, isn't it? But anyway, right. So yeah. So it's actually quite a hard thing to describe. Okay. And I'm fairly sure this one doesn't particularly like cheese. In fact, most mice don't much like cheese. They much prefer bacon or apple. But anyway, right. So when you're describing, you are saying what you observe, what you see. Or if you can't see it, say it's like energy levels in an atom or something. It's what you would see if you could see it. Right, so obviously you can't see electrons going up and down energy levels in an atom. Yeah, it's too small, so you absolutely cannot see it. But it's what you would see if you could see it. Right now, describe in A-level physics doesn't just mean say what you see or say what you would observe, but it also means say everything that you see, including numbers. So you cannot describe a graph unless you give the gradient. You cannot describe the motion of a particle unless you give both the magnitude and direction of the velocity vector. You've got to give everything. Okay, so describe is say what you see or what you observe, but it's everything, including numbers. Okay, that's really important. Most people, they only half-heartedly describe, especially right those horrible questions, the ones that is describe an experiment to show, and you draw this mean miserly little diagram without using a ruler that nobody in their right mind would be able to construct the equipment from, and then you write down that you measure the velocity with a light gate, which doesn't measure velocity, it only measures time, and nobody works out how to measure the velocity from the time given to you by the light gate, and you don't really explain which is the independent variable and which is the dependent variable, and you don't say how you're going to measure them, and you don't say how you're going to change it, which is what all of what you would observe if somebody was to do the experiment in front of you. You have to say it all. Everything, what graph you would plot, everything. Describe is describe everything that you'd see. Everything. It's really comprehensive. Okay, and you mustn't muddle it up with explain, which is key fact consequence. Right, okay, enough. Right, I'll stop yelling at you. Okay, so we go back. Right, the source of green light is changed for one that contains red and blue. For any material, red light has a lower refractive index than green light, and blue light has a higher refractive index than green light. The angle of incidence at the glass liquid interface remains 58 degrees. The angle of incidence at the right, so I'm just gonna, let me make it a little bit smaller so I can get my diagram and the question on the screen at the same time. The angle of incidence, right, okay, so I'm going to draw in the angle of incidence. So I've got to put in my normal, because angles of rays are always measured to the normal. So my angle of incidence there, that one, is 58 degrees. They've told me that it is. Right, now, it then says, describe and explain the paths followed by the red and blue rays immediately after the light is incident on the glass liquid interface. Right, now, you've got to both say what you would see and explain what you see. So right now, this ray in this diagram is green. Okay, I'm going to make it green. Right, so there it is in green. But that what they've said is they're replacing it with a red ray and a blue one. Now, if it's a red ray, let's think about what happens to the red ray first. If it's a red ray, they've told us that for any material, the red light has a lower refractive index. Okay, for any material, the red light has a lower refractive index. So if my sine C is equal to, let's just go with 1 over rather than think about a liquid. Let's just go with 1 over my refractive index for glass, right? If this is lower, what happens to this? Is it bigger or smaller? And I'll put you out of your misery, it's bigger. Okay, the reason it's bigger is because for sine does this, doesn't it? Between 0 and 90 degrees, right, theta goes up as sine theta goes up, or vice versa. Right, now, if this number on the bottom is smaller, then this whole thing gets bigger, which means that sine C gets bigger, which means that C gets bigger. Okay, so my critical angle is bigger. Right, now, if my ray comes in at 58 degrees, but the critical angle is bigger than that, what will happen to the refracted ray? Do you get total internal reflection if your angle of incidence is bigger than the critical angle or smaller than the critical angle? Bigger. Right, now, 58 degrees is smaller than the critical angle because the critical angle gets bigger. So is this going to totally internally reflect or not? Yeah, you are not going to get total internal reflection. Right, in fact, what you're going to get is refraction and a partial reflection. Okay, that's what will happen for the red ray. What's going to happen for the blue ray? Okay, so we're going to get a blue ray coming in. Right, now, for the blue ray, the refractive index is bigger. No, yes, bigger. Which means our critical angle is going to be smaller. It's going to be smaller than 58. So for the blue ray, what are we going to get? Total internal reflection. Yeah, in fact, all of the light will come this way. All of it. Okay, so now we've figured out what's going to happen. Can you see what we've got to write to make sure that we both describe and explain what happens? So we have to describe what happens to the red ray. We have to describe what happens to the blue ray. We have to do both. And then when we've described what happens to each of them, we are going to then explain what happens to each of them. Can you see we've got to do it for red and blue, both describe and explain. So in order to get these 3 marks, we absolutely have to do 4 things. We have to describe for the red, describe for the blue, explain for the red, explain for the blue. We have to do it all. If we don't do it all, we are not going to get all the marks. So what are we going to do to describe? We're going to say the red ray will refract, some light will escape, there will be partial reflection. For the blue ray, you're going to say there will be total internal reflection. No blue light will refract out of the semicircular block. Now I've described what happens, and then I can explain what happens. And explaining includes key fact. Oh, there's a key fact. There's a key fact. There's a consequence of my key fact. And the ray refracts. That's a consequence as well. I ought to put it in red. The red ray refracts. Okay, so then you go ahead and you say that there's another key fact, and the blue ray totally internally reflects. Can you see your key fact and consequences are often an equation in physics? Right, now we have to do everything. We must do it all or we won't get all the marks. But if you do it all, then there's a very good chance you're going to get the marks. Can you see? It's no longer vague what you've got to write. It's really clinical. Okay, so let's go and have a look at the mark scheme for this. This is 3.3. Right, now, can you see some stuff? It's just saying about reflection, but not total internal reflection. Would risk losing marks? Yes, it would risk losing marks. Okay, so can you see the first bit, this is the description. The blue light undergoes total internal reflection, the red light is refracted. Okay, there is the description. The reason, i.e. the critical angle for the red light is more, or the critical angle for the blue light is less, that gets you the third one. Can you see? That's my explanation. Right, now you could do that, or you could do that as well. Right, now, this don't know if the refractive indices change by the same factor. That's because there's that liquid on the top. And of course, the refractive index of both of them, the liquid and the glass, is going to change. Well, if it changed by the same proportion, maybe the critical, can you see, you can't know what the critical angle is then, because you haven't got the refractive index change for both materials. So if you were thinking, I mean, I said, oh, let's just ignore the fact that there's a liquid there. That's what's called keep it simple, stupid. So you kind of go, right, well, there's no air resistance, or right, no, there's no air upthrust. I'm just going to ignore the fact that the string weighs something. I'm going to make sure that my pendulum bob string doesn't stretch. All my wires in my circuit have zero resistance. That's keeping it simple, stupid. Because if you overcomplicate it, it becomes impossible to answer A-level physics questions. So you just go, right, well, I'm just going to simplify it until I can. So I simplified it. I said that there wasn't any liquid there. And all of you let me get away with it. And it was right to, because can you see the simplest answer, the first one, it's basically, let's ignore the fact that there's a second material, the liquid there. Hopefully that has helped you with the main two command words. So explain and describe. And right, the next thing to do is to make sure, especially for the 6 marker questions, that you follow every command word that you're given. So let's pull up, in fact, I hope you don't mind me doing this, Ian, but you put into the group chat, so everybody's seen it already. No, group chat. A question, which was a 6 marker question. So here is the 6 marker that Ian shared in the group chat. And it's not simple. It's not an easy question. But what I want you to do is I want you to look at the command word. Right, so here we've got parallel plates. We've got an experiment. This oil drop has got a charge on it. It's negatively charged. So it's going to be attracted to the top of the, because this is the positively charged plate. So there's going to be a force upwards there, which is QE, which of course is Q, the potential difference, divided by D. What other forces are going to be on my oil drop? Weight, good. Any other ones? Upthrust, agreed. I'm going to do it in a different colour so you can see there's a second upward force there. I'm going to call it upthrust. Upthrust is the weight of the air displaced. Right, now, those are the forces on the object. Right, now, it says when the potential difference is 0, so this has gone to 0, right, that power supply is not there, the oil drop accelerates to terminal velocity. So if V is 0, this V is 0, this E is 0, and the upward force F is 0, can you see that we end up with W up, down, and U up? W down and U up, and W is bigger than U, okay, and you end up with acceleration, yeah, because you get a net force, okay, so there is a resultant force, and you'll get, because F equals ma, you'll get an acceleration. Right, now, why do we get a terminal velocity? Why does the result, W is bigger than U, W's not changing, U's not changing, upthrust is the weight of air displaced. The particle of oil hasn't got any bigger or smaller. The weight of air, thank you, yes, drag. Okay, so drag then increases when?
Velocity increases.
Until, right, so can we write an equation? Can you see that W is down and we've got upthrust and drag up, and when those are equal to each other, can you see that we're going to end up with no acceleration, because F is 0, so A is 0, and you get terminal velocity. Right, now, that's when the potential difference is 0. Right, then it says the potential difference is increased. It's observed that at a particular potential difference, the oil drop stops falling and remains stationary. When it's stationary, what can we say? There's no drag anymore. When it's stationary, what
The
can we
electric
say?
force is equal to the weight.
The electric force and the arc thrust is equal to the weight.
Yeah.
Oh, yeah. Can't ignore here, not when there's terminal velocity going on. You have to allow for air resistance when there's terminal velocity. Right, now, can you see what the command word says? The command is to explain. We've got to explain the motion of the drop. We've got to explain the motion of the drop in terms of the forces. Can you see why I was insisting on talking about the forces? Right, now, we've got to explain the motion of the drop in terms of the forces as the potential difference is increased from 0 to V. Can you see how clear this is? You have to explain that when the voltage is 0, there's a net force down. Can you see what you've got to do? Here is a key fact. This is when V equals 0. Then you get, the consequence of that is an acceleration. And the consequence of that is that drag increases. And the consequence of that is that eventually you get the forces in equilibrium, you get no acceleration. Can you see it's a consequence? And you get a terminal velocity. And that's what happens at 0. But then you've also you must also put into your answer what happens as you increase V. If you increase V, then you increase the upward force that is caused by the electric field. And you really need, it's got rid of it, you really need to make sure that you've included your equations. Okay, those are your key facts. So as V increases, the electric upward force increases until F plus U up equals W down. And when that happens, then the forces are in equilibrium and the particle can remain stationary. Now, can you see how many bits of explain you've got to put in? This is 6 marks. So you must explain the motion. You must talk about the forces. You must do it for both 0 volts and as you increase to V. So basically, you've got to explain terminal velocity. You've also then got to explain why there's an upward force when you increase V until you get equilibrium again. Can you see you've got 2 separate situations? One where it's falling and you get terminal velocity, and one where you've got an upward force and you've got equilibrium despite the fact that it's not moving. And you've got to talk about all these forces. You must mention the electric force. You must mention upthrust. You must mention the weight. You must mention drag, and the fact that drag increases as the velocity increases. You must explain terminal velocity is when your forces are in equilibrium. You must explain that in order for it to remain stationary, your forces must be in equilibrium again. But can you see the difference between the two situations? You've got to explain the whole lot, all of it. Okay, so it was a really good question for you to put in the chat, Ian. So thank you for that. Okay, your homework is to have a go at this. Hopefully that has helped you all with your exam technique. So there's loads more. Go through the essential exam technique. Do it systematically. Make sure you've gone through it all, preferably before your next big test. Okay. Okay, hopefully that helped you all, and I will see you all. If you've got any questions, obviously hang on. Otherwise, that's it.